some facts about bipartite graphs. Yeah. So I will not say many things about bipartite graph, just to understand what it is and two things about it. So first thing is how to test graph by bipartness. How do you think? How to understand is our graph bipartite or not? Please. How to test our graph by bipartness? Yes. Actually, we have just a little thing to do. We have just 4 algorithms right now, yeah? 2 algorithms, Kruskal and Prims, and 2 algorithms by search in graphs, yes? DFS and BFS. So you can just use the exception method to understand what we can do. So we can use, for example, graph first search and DFS search to test graph for bipartness, and how to do it using this algorithm. Yeah, surely. So yeah, we can color just one by one. Yeah, we choose which algorithm you prefer more. For example, DFS or GFS. Let's consider DFS. So we start with one vertex and first color with 1. When we add another vertex, we should change color. Yeah. So here will be zeros. Yeah. And next we will have ones and so on and so forth. If we add some edges between 2 vertices with the same color, in this case this graph will not be bipartite. Yeah? If we have just difference, for example, like this one, so in this case will be bipartite. Very easy. You can choose BFS or DFS. When we have edge between 2 vertices in the same group. So very simple algorithm. Yes, so the complexity of this algorithm the same as complexity for DFS and DFS, and in the connected case it will be all of the number of edges. By the way, in this step, do you understand why this is the same as this one for connected graphs? Why? Yeah, because this should be, for connected graph, will be more or equal than v minus 1. So we can rewrite it just in this for simplicity. Okay, this is testing algorithm, and let's very quickly another. So bipartite graph you can test it by this algorithm, but there is also very simple criteria to understand is your graph bipartite or not. So it's necessary and sufficient condition of bipartite. So connected undirected graph is bipartite. So G is bipartite if and only if it doesn't contain let's very quick proof with theorem. For example, in this direction. If we have bipartite graph, why it doesn't contain odd cycles? Huh? Yes, very simple. If we have odd cycle, we try to color what means nичего. We color one by one vertices, yeah, and we can't color odd length cycle one by one vertices. Yes? So it's very simple. In reverse direction. Yes, and by how? Dramatic number. It's a very complicated thing on this step. Yes. Yeah. So you tell about how construction spanning tree algorithm. Yeah. So we construct spanning tree in our graph because it's connected, yeah, and color each vertex just in this case. Yeah. Then what should we do next? What's the next step? Okay. Yeah, you mean that just by definition. But we can, for example, do it so if you have spanning tree like this one, so then just let's add new edges that are not in spanning tree. And let's prove very easily that this edge will connect vertices with different groups. Okay? Why? Because if it not connects, for example, let's consider 0 somewhere here. Yeah, actually in the tree we have just unique path for between two different vertices. Yes, so we have unique path from the root to this vertex, and for example, to another vertex that we consider. Okay? So let's consider. Let's suggest that we have edges between these two vertices. Let's just calculate the number of vertices. Yes? So it is easily to calculate, yes, that in this case will be odd cycle. Yeah, I hope you understand. So it's very simple theorem. Okay, so this is all that you should know here about bipartite graph. So how to say if your graph bipartite or not? If you see triangle, what you should say? Not. Very simple. Yeah. If you see just triangle, you should certain that it's not bipartite. Very easy. Okay. Let's go further. Let's consider something. Let me open something here. So let me share the screen. Yeah, you can see here is free. So our second thing is about what? I take some hero here, and you see very complex map. I just take this hero and put point, for example, somewhere here, and you see very easily on this very complex map, you see the path between two vertices, this one and this one. Yeah. So our next theme, how to construct these paths. But by the way, I think here something like a star algorithm, very quick algorithm, and I will not say about this algorithm because it uses some heuristics, and it's very complex, or sometimes you can't prove some things about this algorithm because you should know some heuristics about it. So here I will introduce very basic algorithms. First is so-called Dijkstra. So what the task? We have directed or undirected graph, weight graph, and we want to construct the path, the shortest path between two vectors. Yes? First question. Do you know the case where there not exist a path between two vertices? If there is no shortest path between two vertices, but we have a path between two vertices. Any graph. We have path, but suddenly there is no shortest path. Yeah, this is the case. So in this task, there is just one case when we can't do anything. It's something like time machine. Yeah, if you understand these edges like time. Yeah, and if you have, for example, something like this one, you can go here and go through this cycle one by one and go through the path. Sometime at any path what you want. Yeah? So in this case there is no shortest path length, shortest path algorithm. If you consider it's like a time, then you travel from one point to another point. So if you go here, so your time is 0, and go there, by this direction, you will have time -1. And you go to this cycle again, you will have -2. And so on and so forth, so you can here travel anytime what you like. Okay, so in this case, we use algorithm only for graphs without negative cycles. Yeah? It's the first thing that I want to say. Second thing, first, the simplest algorithm, so-called Dijkstra. By the way, if you want, I can change to Russian language if it's common for yeah? Yeah? человек попросил. Ну, да, он может быть запись. Ну ладно, давайте тогда на английском. Okay. The extra algorithm. So this is shortest path. So this is algorithm of finding the shortest path in directed graph, but only for positive weights. Okay? For positive weights. Yeah. So how to do it? It's very simple. Let's consider some good graph. So here I will show you the directed case, but it's also the same for directed case. Let's consider this graph. Here, 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 here. And this one. This is A. Let's note vertices by letters. A, B, C, D, E, F. Yeah? And let's weights will be this one. 1, 7, 4, 1, 5, 2, 7, 1, 6. And we want to construct shortest path from A to F. So let's here write two tables. First table, so or two, we have two arrays. First array will be thing that in the last step will be all shortest path lengths from A to any number of vertices. We will denote this by D. Yeah, I here I show for undirected case. You can just do the same thing. What? D will be all shortest path lengths from A to any number. Will be. We will change. So here with D, and we have A, B, C, D, E, F. And another thing, P, it will be so-called predecessor. So the vertex that will be the previous on the shortest path. Yeah? From if we go through this A. So also we have A, B, C, D, E, F. Yeah. So the first initial step or zero step, we add here 0, here we add all infinities, and here we add something like star to show that we're starting from A. It's just notation that we're starting from A vertex. And here no predecessors, so I will denote it by 1. This one. B1, B1, 0, and so on. So we start with this vertex. Yeah? We can mark it by visited vertex. So we add here, yeah, we consider D0, and we add from, we go through A. If we go from A to D, we add this weight to this mark A. Yeah? So here we change this D for 4, and predecessor from to D will be A. Yeah, so we put here A. Yeah? Here 7, so we put here, we add 0 plus 7. Here we put 7. So if we have the number less than the previous one, we will change it. Yeah, we will change it here and here. Because 7 less than infinity, because in this case we change it. So we go to C from A, we put here A, and here also A, here star, 1. Yeah? And 1, here, 0, infinity, infinity. So this is the first step. Yes, yes, the extra algorithm only for positive weights, only. For directed or undirected case, it's no matter, but only for positive weights. Okay, this is the first step. So we visited the first vertex A. We can, for example, add here line, means that we visited this vertex. Let's choose here in this array the vertex with the smallest number. Yes, it will be B. Yeah. And then we start from the vertex B, doing the same thing. So we can go from B there. So we should go from B to any vertex that not visited yet. So from A we not go here and here. So here will be 5. So we add from this 1, we add 5, and we have 6. Now let's compare it with 7. Yeah? So we add here 6, and we change from C that we go from B. Yeah. Yeah. And here will be 8. So 8 in E less than infinity, we put here 8 and put here B. So that's all. That's all edges from B, and we visited B and add line here. So this thing will be the next step. Be free. Well, this will be 0 each time. Let's find the number not visited yet. The smallest one, it will be 4. It will be D. Yeah, here. Two edges to C will be sum. 4 plus 1 will be 5. Yes, and will be less than 6. So here we put 5. Here we put D. And here will be what? 4 plus 6 will be 10. So we put here 10 and also put here D. We in the case D. The mark corresponds, the number corresponds to D will be 4. We add to 4, 1 and 6. By the way, how many here will be in this algorithm will be rows? In the common case, 1 row corresponds to 1 visited vertex. So, how many rows? Yes, n. Yes, so let's just write. So D4, D5, and I think that's all because the last will be n. So P4, P5. Here 0, 0. Here star, star. Let's go far. The smallest one will be 5. Yeah, we just only have 3 not visited. 5, it will be C. So from C, here we visited vertex, here visited vertex, just one edge here. So this will be 5 plus 2 will be 7 in E. Here we put it here. So we go from C to E, and we also here change it by C. Yeah, it's just one thing, and we visited C on this step here. A, D, A, D. And the last one, so you see here it's E. By the way, if F will be the smallest one on some step, yeah, we'll stop over here. Yeah, because in the next step will be more. Yeah, but this is not this case. We go from E, yeah, the last one, and we see that it will be 8 here. We put here E, and that's all. Yeah. So this is the result. What we see here. This is the length for shortest path length from A to any another vertex. Yeah. So to B, B, C, D, it will be just H. Yeah. And for another. So how to reconstruct the shortest path if we know this area? Okay, yes. So, yeah, please, what will be the shortest path? From A to F. So the last one will be F, yeah? E. Okay. Yep. Yes. Yes. So this will be the shortest path. So yeah, it's very easy to construct it from this. Also, what we have here, we can construct so-called shortest path tree, or in this case, if the graph is connected, shortest path spanning tree. What is it? This is just this thing. This thing corresponds to the shortest path spanning. Let's just color the edges. Yeah? Also we have some colors, it's very good. So we go to F from E, so this one. CE, CE, AD. Yeah, I think this will be. No, I'm wrong. Here is it not. Yeah, I think that's all. So this is shortest path tree. What also it gives us? It gives us, we know that in tree there is unique path from each two vertices. So there is also unique path from A to any another vertex. So the path from A to any vertex through this spanning tree will be shortest path. Yeah? So we go from E to F, so we add the edge EF. We go from C to E, we add an edge CE, and so on. So it's just edges of spanning tree. Yeah, and it is the extra algorithm. Okay, any questions? No? Yeah, good question. Complexity. What is complexity? But we can easily see by this algorithm because the worst complexity will be just like with what? E plus v squared. Yeah. So what it is? It's the same like v squared. Yeah. Why? Why it is? Yes, yes. Because of complete graph. Yeah. Because in complete graph it's v by v minus 1 divided by 2 and so this is. Yeah. But we can, using some structures like binary search tree or heap and so on and so forth, we can increase it by this thing. E plus v on log v. This will be that. Okay. So using specific structures in this algorithm, I will not go through details, but if you use binary tree or heap, you can increase complexity. Improve complexity. Yes. Okay. So it's our very, very simple algorithm for positive weights, and you can ask, what will we do for the negative weights? This case will be so-called Bellman-Ford algorithm. Bell, double L, 1, 4. What is algorithm? So let me not show you how it works. It's the same as Dijkstra algorithm, but here you should do, here you visited, so you started from vertex, yeah, and try to add edges from this vertex to not visited. In Bellman-Ford algorithm, you should do this procedure by all the edges anytime, any step. So, what I mean, you write all of these edges, yeah? And you see, for example, this step. Yeah? You take some edge, for example, CD. This weight is 1. And consider this area. So you should take this from C, add 1, and compare it with the number in D. Yeah? If it is less, then you change it here and also change it here. But for all edges of your graph, you should do at each step for all edges this procedure. Okay? And the number of steps will be v minus 1, like in this case. So you should do all of the steps for any edge, and for the number of steps times the times is v minus 1. V minus 1 times you should do. Yeah. And finally you will have this. Yes. In the final step you see the same thing. Okay. By the way, I said about spanning tree. And what will be if we consider directed graph? What we will have something like this spanning tree. What we construct using this algorithm, if our graph is not undirected but direct. What will be? Will be almost. But how we how we uh, how we define, how we call this thing, this special thing, because it's not just a range. Also, by this algorithm, we can go from this vertex A to any another vertex in directed way. And what will it be? How we call it? In Russian, we call it деревообразование. In English, it's called arborescence. Arborescence. So, actually, Russian word деревообразование, it's the translation from this one. So, maybe not very good in Russian, but in English it's called arborescence. That it is oriented tree, in this case spanning tree, oriented spanning tree, and we can go from the root to any node by it. Because, for example, we can have this also oriented tree, but we can go through. So, this algorithm and this algorithm gives us also spanning directed arborescence, so just spanning arborescence. Okay, so in this case, it's more easily to say what will be the complexity of this algorithm. What will be the complexity of Bellman-Ford algorithm? No. Yeah, well, you can say that it vertex in the third degree, but it just v multiplied by e. Yeah, because on each step we correct this algorithm by choosing all of edges. Yeah, and the number of steps is very small. Okay, so we have more complexity, but if we have more complexity, we suggest, so maybe with something missing. Maybe Bellman-Ford algorithm give us something in addition. And it is also if you, so let's do the Bellman-Ford algorithm for v minus 1 steps. And after that, also do this algorithm just addition step. So we do this algorithm by v steps. What we can see here. So if our graph is good, if there is shortest path, so it's very meaningful because we will have the same here and here. But if we have not very good graph with negative cycle, we will see that in this case something should change. Yes, you are yes, but it can spend many steps to find that. No. Also, by this step, you can so with mark cannot be changed. So if you want to see here something negative, you should do many steps. But something should change if you have negative cycle here. Yeah. So Bellman-Ford algorithm also help us determine negative cycle in our graph. Yeah. So it's very good. You just do it one more step, and you will see. So in the first step, you shouldn't know if your graph have negative cycle or not. You just can do it for any graph, and you will see. Yes. Ну, я так и сказал, yes. Yes. No. Just by additional one step, we determine if there is negative cycle in our graph or not. No. The extra algorithm only for positive weights. But if you have negative cycle, you have negative weights. So this is the case that you just can do it for any graph with algorithm. You can use it for any graph. And if you do it one additional step, you can say if this question is correct or not, or if this graph has negative cycle or not, just by one additional step. And also, let me note this thing. If here something changed, then here should be also something changed. Yes? And if we consider what letter will change by this additional algorithm and go from to opposite direction, from this vertex to previous one and previous one, like trying to calculate shortest path. What we will find? Negative cycle, yes, that's right. So also by this algorithm, we just not only determine, but say where is it? Where is negative cycle? By using these processors. Yeah? No, we can. Yeah. You thought about the extra. The extra only for positive weights and Bellman-Ford for any weight. Bellman-Ford for any graph. Surely, because it's only for positive weights. If you have negative cycle, so you should have negative weights. Yes, the algorithm almost the same. But the most important thing that here you starting with visited vertices by edges only adjacent to this vertex. But in Bellman-Ford algorithm, you go at each step for all of vertices in the graph. But you update here elements the same, like in the extra. Okay. So yeah, very good. Let's go further. This algorithm is to find just one or n paths, n shortest path from our first vertex to another. Let's try to find all of possible ways, shortest path ways, shortest paths from any two vertices. Yeah? So next will be how to find so-called path matrix, shortest path matrix. Yeah? So you understand what is shortest path matrix. Okay? It's just length of shortest path from one vertex to another. So in undirected case, this matrix will be symmetric. And in undirected case, so in undirected case it will be symmetric, and in directed case it can be symmetric or not. So, yeah. Okay. Let's do it. So there is a very simplest thing, so-called Floyd-Warsaw algorithm. What is it? You take, so let's denote this shortest path matrix by this. And you start with what? You start with zeros on diagonal, and here infinity. And the simplest way is so-called brute force way. So you take this algorithm, and for each two vertices, for each three vertices, V, W, and Y, you consider D, V, W, and consider D, W, Y, and D, here, V, Y, Y, W. And you compare the sum of them and this one. Yeah? So let's consider that, for example, V, W, and Y are adjacent. And for each pairs, you consider all of those things, and if this sum less or equal with one, you update here. So it's like brute force. You can consider all these three things, and you should check all these things. Yeah, it's very simplest algorithm, but I think it's not very interesting. So let's say in our algorithm, let's talk about another algorithm, more smart, I think, more interesting to me, so-called Johnson's. Yes. All of three vertices. Yes. So first step of this algorithm is use Bellman-Ford algorithm for some vertex, for example, from A. Yeah? And in this case, we will find d of V. Yeah? So the distances from our vertex A to another. To any vertex there, V from then we check if this graph have negative cycle or not. If it's have negative cycle, then we say sorry, we can do it. If it's not have negative, it is not, it doesn't contain a negative cycle, then we do this thing. We change, so we have some weight between V and W vertices, and we change this weight. Let's denote it by U, and W will be the weight. So we change this weight by this thing, dV minus dW. We change the weights in our graph by this procedure. We'll see why it is. We will see. So yeah, the first question, why? what we will have. For example, let's consider some something like this one. And this is the vertex A. We said, yeah, that we said sorry, yeah, yes, I not right, yeah, but not this thing. Yes, here should be, we change weights, so here should be VU minus this one. Minus. Yeah. Yep, sorry. Yes. Yeah, sure. Yeah. We said what? By Bellman-Ford algorithm, we constructed spanning tree, spanning arborescence. Yeah? What we can say about this arborescence after changing weights in this manner? We change all of weights by this procedure. Yes. Yes, if it is in arborescence. Yes. And what you can say, what will be the new weight between these two vertices? If VU is the edge of this spanning arborescence. dV minus dV. Yes. Minus here, minus also. So let me answer this question. In this case, it will be 0. For spanning arborescence, all weights will be 0. From A, yes. From A, yes. 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 Will be 0. So for spanning arborescence will be 0. Not vertices, edges. 0 will be for any edge that corresponds but belongs to spanning arborescence. From A, yes. Not one step, but through whole arborescence. Yeah. For example, here and so on. It's the first noticed. Second noticed. Second, W in this case will be more or equal 0. All weights will be non-negative. what is d of v? Yes. And what is d of u? Yes. You have a, you have shortest path to, you have shortest path to v, and you consider the w between v and v, yes? This one. If with shortest path is that, you will have 0. Then it will be more. Yeah, more than 0, not 0. Yeah, so I think you should think about it, and you will see. Okay, so we construct new graph with non-negative weights, and also we have 0 weights through the spanning arborsis. Yeah? So you can add here through this spanning tree, and if you consider this I said that Dijkstra algorithm works with positive weights, but it also works with non-negative weights. With 0 weights it also works. So you can use here Dijkstra algorithm. And this is Johnson algorithm. So for any 2 pairs of vertices, you use Dijkstra algorithm to find this shortest path path length matrix. Shortest distance matrix. And you find another. So that's denoted by d prime v w for this new graph. And how do you think how to construct the initial, the distances for initial graph? We don't know d. D you mean with t, but it's array. This is array and this is matrix. This is the distances only from A to n in our vertex. Minus d prime. Not actually, but yeah, the intuition is the following. Yes, you're right that you should just add this thing to all of this here elements. And that's all. Yeah. So here you subtract and then you add, and you will have the shortest path matrix for all that. This is all about those two. And the complexity, if you very accurate calculate the complexity, the complexity of methods that we are using, you will have something like this one, v plus v times v of v, something like that. Yes. Sorry. Let me check again. Let me check. Check. Yeah. Check. 1 minute. I will check. Yeah, you are right. Here plus, and in this case we should subtract. Yeah, that's right. Sorry. Whew. This is all what I want to say about algorithms for searching shortest path length. Let's go further. Let's tell. So all of these things that I said before will be about combinatorics. Yeah? It's combinatorial methods, combinatorial algorithms. Now we want to add here some geometry. Yeah? So we will say we will want to draw the graphs on the plane and so on and so forth. In this case, we go to the planar graphs. Yeah? Do you know what is planar graph? Yeah, sure. So planar, if we can represent it on the plane without intersections of edges. So yeah, if there is some representation of this graph. So graph can have many different representations and also many planar representations. Let's consider some cases. For example, 3 planar or not planar, and second, right? Because we can do it step by step. We can, using some algorithm, we can add edge one by one. Second, let's consider some complete graphs. For example, K2. Yes. K3. K4. Yes, it's also fine. Good. K1, 2. Yes. K1, 3. K2, 3. Yes. And all another are not. So K5 not. K3, not. By the way, K3 is very famous task about villagers. So, for example, we can reformulate it's like in the terms of villagers and supermarkets. Yeah, we have 3 villagers, 3 houses of villagers, and 3 supermarkets. And the villagers very hate each other. They do not want to do not want to see in any case in our village. So you want to find all of the paths from each villager to each supermarket, and it will be not planar. So you can do it. You can do it. So let's prove some of these facts. For example, for the graph K5, and also yeah, you can consider M with M over to 5, and A and M with M over to 3. Yeah, also not planar. Let's prove it using so-called Jordan curve theorem. Yeah, and Jordan curve theorem have many different formulations, so we will use it in this the formulation in the following formulation. So any simple closed curve C divides the plane for two disjoint subsets. So so there are two disjoint subsets here. Yeah? And any curve starting from the point from one subset to another point should intersect to this curve. This is a curve C. Okay, so if it is divided by two parts, we can denote one part by int. So it's inner part and outer part we denote by out. So okay, let's use this theorem to prove that, for example, K5 is not planar. Let's consider some cycle of K5. Yeah, V1, V2, V3. We have this cycle in K5. This cycle is closed curve. So there is two parts of this initial part and outer part. Inner part and outer part. So, let's suppose, without loss of generality, that V4, so V4 should be in inner part or outer part. That's without loss of generally that V4 in inner part. So here, V4. So let's denote three cycles. C1 will be V4, V3, V2, V3, V4, V2. Yes, this. C2 will be V1, V3, V4, V1, and C3 will be V1, V2, V4, V1. This is three cycles. Okay, so let's consider V5. Let's consider V5. If V5 belongs to inner part of cycle Ci, then V5 should intersect cycle Ci by Jordan curve theorem. Yep. Thus, V5 belongs to outer parts of any Ci. Yes? Yeah, we first we suggest that K4 is planar, yes? So we can draw it in the plane without intersection, yeah? So no, we can consider the case when the vertex belongs to any here. if V5 belongs to some initial part of Ci, then VSH should intersect to Ci by Jordan curve theory. Yes? And it will be a contradiction. Thus, V5 for any I belongs to outer part of all Ci. Yes? So, V5 belongs to the intersection of outer part of Ci. Yeah? And that's all. So it's V5 and then V4, V5 should intersect with, very easy, just by using Jordan curve theory. So we will do the same thing. For example, what I you want? 2. Simple. C2, it means we take V1, V4, V3. What this is our side. So V5 here. So V5, V2 should intersect with. So in the same manner, if you want, you can practice just to using this theorem for the case K2. Yeah. No, we just change all inner parts to outer parts. If before outer part, we consider 3 cycles. Okay, so we see here that we have some inner parts of closed curves and outer parts. And in the graph, we defined different things. So something will be very common, so-called interface. It's a face of planar graph with some representation. Bounded. So it's inner part bounded by simple cycle. That not contains any analogous. And also we have some special thing, so-called outer part, outer face. What is it? Outer face is the intersection for all simple cycles, outer parts of all simple cycles. Okay. We will call it outer face. So our graph have, so all faces, this is all will be faces. And I think next time you will see why I called this also face. Because actually it's very, actually the answer of this question is very simple. That you can consider a graph not in the plane, but in sphere. Yes, in this case in sphere, outer face also will be bounded by. Yeah, sure. So first very famous theorem is so-called Euler theorem. I think all you know what it's about. What's Euler theorem? Yeah, please. Yeah, we will go it in more simpler way. So for any connected graph, for any planar graph, planar connected graph, we will have this thing, the number of vertices minus number of edges plus the number of faces, where will it just two. Yeah, or some further characteristics, but we will here prove very simple. Yeah, how to prove it? Yes, by what? Induction is very good suggestion, but by what? Yes, yes. I prefer the induction by the number of faces. Yes. So if we have just one face, what will be the graph with just one face? One face means that we have no simple cycles. Yes. We remember that no simple cycles means that we have no cycles. If we have no cycles and connected graph, it will be what? 3. So if we have just one, so the number of faces will be just 1, so we have 3. And what is the number of vertices and what is the number of edges? And minus 1. Yes? So we see here. The base is very simple. So the next step. If we know this theorem for all graphs with k faces, let's prove it to the graph with k plus 1 faces. We can do more things. We can consider outer face, and if we have not just one face, then we also have inner faces. So we have an edge that bounds outer face and inner face. If we delete it, we will have the graph with faces minus 1, and for which we know induction. Yes? So that's it. Very simple. Okay. I said here connected. What will be if I said it's not connected, but just planar? If will be some changing here. Maybe, but it's too complicated. If it's not connected, here will be 1 plus c, where c is the number of components. Why? What is with 1? This is 1, is outer face. This outer face is common for any of components. Yes? And if we will sum of these things for components, we will have here just 1. Because we have also 1 outer face. 1 common outer face. For example. Okay. So we can also do very good suggestion for planar graphs. So for planar graphs, turns out that the number of edges, yes, we previously we said that if we consider some algorithm and complexity of this algorithm, if it's not, if it's connected graph, we can this thing change to that thing. Yeah? But for planar graphs, we can do the opposite. Why? Because we can prove. So, some polar that number of edges less or equal 3b minus. That means if we have algorithm for planar graph, we can change it just by O of number of vertices. Because of edges, they are bounded by the number of edges. So how to prove it? This thing. How? Yes. And but not two vertices, two edges. Any edge, yes, it belongs. So let's consider, let's delete all vertices that belong some, yes, no, no, no. Yeah, yeah. Yes, yes, you're right. So this is, so we can show easily that we have this one, yes, E more equal to 3f. Yes? And then just using Euler theorem, we put here f by here and okay. So at the last, let's also prove some corollary. Yes, we will do it very. Every connected planar graph, has a vertex of degree at most 5. How to do it? So planar has I any connected planar graph has the vertex of degree at most 5. Yes. Yes. Yeah, you're absolutely right. So we're using two things. First is this one, and second is handshaking them. Yeah. So this one is corresponds to the number of sum of degrees. We consider that all of degrees equal or more or equal 6, and then we will have complete. So yeah, that's all for today. Yes, I want to ask, say the last thing. about the home task. First, if you not send me some mail, please send, and I will give you a graph. And with graph and task, and with task, you should do on the paper, so by hands, not using computer. You should do all calculations, and also you should send me all your calculations. In this case, I will see that you do it and how you understand. And also, I suggest you to do it early, because you will have different tasks, and previous task will connect it to the next task will be connected to the previous task. If you have mistake at previous task, it will go through and can go through many tasks, and you will have many mistakes. So I will check, and I will tell you if, for example, here you have some mistake. No, I don't want to send my mail to chat. I can, yes, I can write it here. And by the way, yes, the deadline is for the starting of second module. So the last day for home task will be the previous day of the ending the first module for my part. I don't know. It depends on the